Okay, so in this video, we're going to look at multiple regression in general, and then performing multiple regression in Excel using the data analysis toolpack. Now, in general, multiple regression is typically done as multiple linear regression, but the transformations that we discussed in the intrinsically linear video earlier, we can also use those same kinds of transformations to make non-linear multiple variable models. We're going to set that aside for now, but it's worth knowing that everything we've talked about with the simple linear regression, we can apply to individual variables in a multiple regression model in order to make a very complex situation. Now, even multiple linear regression, though, we've come up to sort of a barrier in terms of being able to visualize the entire model at the same time. So we're going to have some visualization issues. We're not going to be able to create things from the scatter plot the way that we had before, but we can still perform the mathematics. In fact, the mathematics for multiple linear regression is basically, if you're doing the linear algebra components, are very similar to each other. There's basically one formula that they all use. Things only become complicated when you don't know the linear algebra and you have to derive formulas with summations and things like that from individual observations for every possible configuration of 2 variables, 3 variables, etc. But the general form of a multiple regression model, again, assuming linearity, is we have an intercept when all the variables are equal to 0, and then we have slope coefficients times the input variables, each one of them. There can be an unlimited number of input variables in principle, but they will vary from problem to problem. Sometimes we'll have only 2, sometimes we'll have 6, sometimes we might have 56. It just depends on how much each of the variables is contributing to the overall model, whether it's reducing the amount of variability we have, how many observations we have, and so on. So there's going to be a lot of analysis that we're going to have to do, and we're going to talk about some of the more complex ones in terms of model selection in a different video than this. For right now, we're just going to set up sort of the basics and then talk about some potential concerns that we might have to deal with. Now, this is our basic model. Now, as I mentioned, the intercept, the beta naught, that is the assumed to be the value of y when all of the coefficients are equal to 0, or all the variables are equal to 0. As with some of our previous models, this is not necessarily something that we can interpret all of the time. Even in our quadratic model in another video, we saw that the constant was negative, and you can't have negative percentages of lighted moon displayed. So sometimes they don't make sense. Sometimes it's impossible for all of the variables to be equal to 0 for a number of reasons. If we're talking about years, this might be well beyond the range of the data that we've collected. So as with general linear models, the intercept is a value that makes the equation work typically, but it might be interpretable or it might not be interpretable. In terms of the remaining beta coefficients, the beta sub I are the slope coefficients for the x sub I variable. So beta 1 goes with x1, beta 2 goes with x2 typically. And essentially what this means is that if we hold all of the other variables in the equation constant, then the value of y will change by this coefficient amount when the corresponding x value increases by 1. And so we'll talk about this after we have a model to construct. But this interpretation is, again, going to assume that everything else in the equation remains constant. That's an additional assumption we have to make. And then we can focus in on just the change from that one variable. Now, and as we saw with the polynomial model, because this is not a simple linear model, there is no linear correlation coefficient. In order to sort of create an equivalent one, Essentially, the multiple correlation value is the square root of the R squared value. The R squared value, as you may recall, is basically an explanation of how much of the variability we've accounted for. And so because in the sort of simple linear case, that is the square of the R squared, they've sort of back constructed this multiple correlation. But they only give positive values for this. There's no negative values for this because some of the slopes might be positive, some of the slopes might be negative. And so, and it's a combination of relationships between all of the variables. And so that's something that we want to sort of keep in mind as we go through this analysis. We can kind of think of it in the same way, but when dealing with these nonlinear and complex models, I personally don't look at the sort of correlation so much anymore as thinking of it in terms of the R squared value. All right, so let us go to Excel and think about some things that we have to consider for these models. So I have some data here that has a couple of different variables in it. And what we would like to be able to do is actually predict the evaluation that the students give the instructor based on the other variables that are in the model. Now, the instructor variable here is just a number that's in place of the person's name, so that is not one of the variables we're going to consider. And we have these other two variables on whether they have office hours or whether they actually hold their office hours, the number of articles they've published, and their salary. And we're going to try to predict their evaluation score. Now, I'm simply making that selection for this example. We could certainly try to use these other three variables to predict their salary, but I'm more interested in looking at how do we predict those evaluation scores. All right, so one of the things we have to keep in mind when we do multiple regression is that all of the X variables have to be contiguous with each other, and then the Y variables have to be sort of separate. They can't be sort of in the middle like this. So what I'm going to do is I'm going to copy and paste some of these. The office hours are 0 if they don't hold them, 1 if they do hold them. And then I'm going to copy these two. So these are all of my input variables. They all go together. And then since I'm predicting the Y value, I will put that last. And one evaluation that we can do before we go to the graph is, or before we go to the data analysis tool pack, is we can look at the correlations of all of these variables with each other. And so let's actually look at that, the correlation. The correlation function is going to build a table of correlation values of any one variable in our data with any one other variable in our data. These are grouped by columns. The labels are in the first row. The output range, we are not going to put way over there. We're going to put right here. And one of the concerns that when we do multiple correlation is that a multiple regression analysis is that we need to be careful about whether some of our input variables are potentially collinear with other input variables. If they're not collinear, then their correlations with each other will be relatively small. And if they are collinear, then they actually are already giving much of the same information with each other. And so there's one of those variables is not necessarily going to contribute very much to the model, and in addition to the other variable. And so in terms of the evaluation, we can look down here. How does the evaluation correlate with these other values? Office hours doesn't correlate very highly, which is surprising. Articles, about half a correlation. Salary, about a half a correlation, 50% or so. Now, one thing that is notable here is that articles and salary correlate highly with each other. And that is potentially problematic. We'll build the model and we'll see what the consequences are, but that would be a correlation that is high enough that that could be an indication of a collinearity problem that could show up in our model in terms of using these other variables to predict evaluation. All right, so now that we have our sort of initial assessment, what we want to do, we could construct individual scatter plots for each one of our variables relative to evaluation. So we could do that. One reason that we might want to do that is in order to, and I'm not going to necessarily do the axis labels here, but I will say which variable I am plotting. One reason we might be concerned about doing that is to know whether or not there's a linear relationship in the data, or if the data is potentially nonlinear, where we might want to go further and make some transformed variables. Discrete variables always look funny on a graph, and so I, don't read too much into this necessarily. So charts. This was evaluation versus articles. And again, this data is discrete, so you can see how they kind of line up here. But there's enough of it that doesn't look too bad. There's probably some sort of linear trend in there. It's not very significant, but there might be one. The evaluation values, of course, are very small, so we wouldn't expect the slopes to be very large. And then finally, and again, I'll just pull this all the way down here. Evaluation versus salary. And again, we can see some sort of a linear trend, slight positive increase, which correlates with our correlation analysis. We could adjust the spacing here, but I'm going to leave it the way it is because we're just looking at this case, not necessarily to have a brilliant final graph to share with outsiders, but just sort of a preliminary look at the data to make sure that, yeah, it's linear. It's not doing anything super funky. And then now what we can do is we can do our analysis of all of the variables put together. And so we're going to go back and do regression. And the Y input range is the evaluation column. And then the X input range is all of the input variables that we're going to use, all three of them. Where it's not constant is 0. Output range, where are we going to stick this? This seems like a good place. And let's do our residual graphs. And just double checking everything. I highlighted the labels, the label box is checked. So, okay. All right, now as we noted when we did the polynomial models, every input variable gets its own residual graph. And so we'll analyze those individually. All right, so let's look at the general model. Our model p-value is definitely less than 0.05. So something in our model is good. It's doing a good prediction. I should not say necessarily doing a good prediction, but it's doing a statistically significant prediction. Our R squared value is not good. We're only explaining basically 30% of the variability in the evaluation scores using these other three variables. Let's look at our residual graphs for each of our variables. And there's one for each input variable, the same residuals plotted against different X values. Again, the discrete office hours one, where we have only 0 and 1, this is going to look weird. But the main thing we want to look for here is, does the variability appear to be about the same? And, you know, the 1 does look a little bit wider, but I don't think it's like meaningfully wider. But we have only 2 input values, so it's sort of hard to tell. The articles, again, it looks pretty random. It doesn't, there's only a few values out here on the end, so it's a little hard to say if this is just, these are influential points, or if the variance is decreasing, or if it's just that there aren't a lot of them. And then, but if we look at salary is really all over the place. This is a good residual graph. It's definitely pretty random. There's no patterns and nothing really concerning about what we're seeing here. And then let's look at our analysis in terms of the coefficients, and let's look at our p-values. And what we see, I mean, this is a pretty low R squared value. Our model test is also low, but if we look at the p-values for the individual coefficients, we're not really getting very far. The articles coefficient, we saw there was a high relationship with salary, that collinearity problem. We are definitely getting a signal here that suggests that this p-value is way too high. We should not include it in the model. This is something that we're going to worry about in a future analysis, but typically if it's over 0.05, you would want to remove it from the model. Now, in fact, as it turns out, all of our coefficients here are way too high. They're all over 0.05. But the thing is that, as we'll see in the backward selection process, you don't want to like go and dump all of your variables just because you have one analysis that has them all over 0.05. As you remove one of these variables that's not contributing, that will tend to change the p-values for the other values. And these are both sort of close to 0.05. It is possible that as we remove this coefficient, that one or both of these will drop below 0.05, and then we would want to retain it. But that is a sort of model selection process. If we wanted to just construct our equation from all of the variables that we have available to us, then the coefficients for our model are listed here. So again, if their salary is 0, which is again not a meaningful value, they have published no articles and they do not hold office hours. This suggests that they would only earn $2,500 because the salaries were in thousands of dollars. That's obviously not a quantity that's interpretable. But we can interpret these other coefficients. As you change from office hours to no office hours, this suggests that your evaluation score only goes up by 1/4 of a point, by 0.25. So whether you hold office hours or not, apparently the students are not penalizing you for not holding office hours, which I find unbelievable. But the number of articles you published only increases your evaluation score by 0.01. So basically not at all. There's no relationship between, almost no relationship between the number of articles you publish and your evaluation scores. If you publish a lot of them, like people out here on the end, then now your evaluation score apparently is going up by quite a bit more. So you can gain a whole half a point just for being famous and having a lot of articles out there. But any one individual article is not going to change your evaluation score by very much. And then similarly for salary, as your salary goes up by $1, your evaluation by $1,000 in this case, your evaluation score is not going to go up very much. But if it goes up by even by $10,000, which is 10 units on our salary scale, it's only going to go up by 1/10 of a point on your evaluation score. So again, there doesn't seem to be a strong correlation between how much you're paid and what your evaluations are, which I guess the students probably wouldn't even know how you're paid, so that would make sense. All right, so that's our analysis. Again, we will continue with sort of what do I do from here, but we wanted to look at the individual p-values and the confidence level output, the sort of more advanced statistical analysis that comes from doing our multiple regression basics.